Morning, folks. Hey, listen, there is that assessment that you'll need to take online. Remember, this is for 5 points extra credit. You get it or you don't. You do it or you don't. So please take that. It's posted on Tutor. I'll send an email out about it later. But if you go to your Tutor main page, it should be on there. And please do spend time on that. As I said, everybody gets credit for it. But I really want you to spend some time thinking about the questions and answering them to the best of your ability, okay? And then we'll have our test on Monday. It's going to cover, since the last exam. We just have a little bit left in this chapter. We have 3 topics. We have temperature scales, linear expansion, and the ideal gas law. We might actually make it through all of that today. So we'll see. It's stuff that you've seen before mostly, I think. So let's look at thermometers and temperature scales. You just need to be familiar with the different ways that we measure temperature. You can measure the volume of a liquid. That's the most common way. That's what we use in a mercury thermometer. And we'll talk about this later, but when a liquid or when a material heats up, it expands. And that's what happens in a mercury thermometer, that when it heats up, that little bubble of mercury or alcohol, whatever's in your thermometer, heats up and it expands up the cylinder. But you can measure temperature in other ways. You can measure the length of a solid. In some thermostats, like in your home, we'll use this, and we'll talk about this in just a bit, but if you have a thermostat, one of the old kinds with the dial on it, you pull it off and you see a coil of wire inside of it. That's the kind of thermometer that we have here, where it changes length according to the temperature. You can also have the volume of a gas at constant pressure. You can use that to measure the temperature. And this is based on the ideal gas law. The ideal gas law is PV equals nRT. So if I have constant pressure, that means P, N, and R are constant. So if temperature goes up, that means the volume goes up. And in a similar way, we can have the pressure of a gas at constant volume. So these two methods to measure temperature are very similar, just based on the ideal gas law. And then finally, or a couple others that you don't see as often, is an electric resistance of a conductor. If you go into graduate school, you might encounter this. This is sometimes called a bolometer. And all it is just a piece of metal. Usually it has some sort of cone around it, and photons will come into that little piece of metal and cause it to heat up, and then it'll change its resistance. You can see this in other things too, like in kitchen thermometers, for example, where you have these 2 little wires and you stick it into a chicken or whatever, and it measures the change in temperature causes a change in the resistance of the metal. We'll talk about that next semester some more. And then finally, you can look at the color of a body, color of a very hot object. And this is how we measure the temperatures of stars. So stars have different colors. They have different temperatures. They have different colors because of those temperatures. Also, like if you've ever seen a fire, how different parts of the fire are different colors. You have blue and orange and red and yellow. What's the hottest part of the fire? The blue part is the hottest. So if you look at very hot objects, they'll have different colors according to their temperature. Well, like I said, we use this for stars, to classify stars. Obviously you can't measure their temperature, but you can measure the light that comes from them. Okay, let's look at so just be familiar with those. You'll have some questions probably about, which of these is a proper way to measure temperature. Just sort of be familiar with them. You don't have to know all the details of those scales, but be familiar with them. You do need to know the details of the Celsius, Fahrenheit, and Kelvin scales. You need to know what they're based on, and you need to know how to convert between those 3 scales. The formulae for doing the conversions are on the formula sheet, so don't bother memorizing those, but you also need to know what those scales are based on. The Celsius temperature scale is based on the boiling and freezing points of water. So on the Celsius scale, we give the boiling point of water up here at 100 degrees Celsius. And then we have the freezing point of water down here at 0 degrees Celsius. And so we have this set distance between the freezing and boiling point of water, and there are 100 increments between them. And if you have 2 points on a scale, then you can set the temperature at any point. So we just base that on the boiling and freezing points of water. The Fahrenheit scale is very similar. It's also based on the boiling and freezing points of water. The only difference is just the values that we ascribe to those. I don't really know the history of this, but the freezing point of water, of course, we set at 32 degrees Fahrenheit, and the boiling point we set at 212 Fahrenheit. And then that allows for, what, 180 increments. So here we have 180 increments, or 180 degrees between the boiling and freezing points. 180 increments, or you can think of 180 degrees. That's just 212 minus 32. Isn't that right? Did I do that right? Yeah. And here we have 100 degrees. All right, so the size of the Celsius and Fahrenheit degrees are different. Which one's bigger? Which one is a bigger change in temperature, the Celsius or the Fahrenheit? The Celsius is a bigger change in temperature because there are only 100 degrees between the boiling and freezing, whereas there are 180 degrees between the boiling and freezing of in the Fahrenheit scale. Useful to know just some basic, sort of typical temperatures. So if I have a 70-degree Fahrenheit day, that's about what in Celsius? Anybody know? It's about what? It's about 20 degrees Celsius. You can calculate that with this conversion factor. So if I put in my Fahrenheit temperature and solve for my Celsius temperature, I can have a direct conversion between those two. All right. Probably not going to have to do that, but I might just ask you for some sort of typical temperatures. Two temperatures that you should probably just know are the nice day, sort of typical temperature of a day of 70 degrees. Also, what is the temperature of the human body in Celsius? It's about 37 degrees Celsius. So you can calculate those, but it's also just to sort of have those numbers on the tip of your tongue. So that 98.6 degrees Fahrenheit is approximately equal to 37 degrees Celsius. All right. And then you also need to know the Kelvin scale. The Kelvin scale is our SI unit. So anytime we're using the Kelvin scale, I'm sorry, is this too fast? I think I've had temperature scales before, so I'm not going to go on it. All right on that? Okay. The Kelvin scale is the SI unit for temperature. So whenever we're using units, you always need to check your units, but most likely you're going to need to be in the Kelvin scale. The Kelvin scale is based on a completely different set of data. It's based on the on absolute zero and the triple point of water. And absolute zero, I think there was a movie called Absolute Zero some years ago, but this is the lowest possible temperature. It is the point when all atoms cease motion. They just stop moving. And so you can't really reach that temperature. It's sort of like a theoretical limit. But if I could take an atom and stop the electrons from moving around and stop all the nucleons from wiggling around like they do, then that atom would be at a temperature of 0 degrees, or 0 Kelvin. By the way, when we talk about Kelvin, we don't typically throw in the degrees. I don't know why, but we don't use Kelvin. Or we don't use degrees. We would just say 0 Kelvin instead of 0 degrees Kelvin. So it's the lowest possible temperature at a pressure equal to 0, which is a vacuum. The triple point of water This is a particular temperature and pressure when water exists in all three phases. So at this particular temperature and pressure, water exists as a liquid, as a vapor, and as a solid all at the same time. It's the temperature just slightly above the freezing point of water. I think it's like 0.1 degrees Celsius. Yeah, the triple point of water, the temperature of the triple point is equal to 273.16 Kelvin, which is equal to about 0.01 degrees Celsius. So we have this scale for the Kelvin, which is based on absolute zero, that's T equals 0 Kelvin, and it's based on the triple point of water, which is T equal 273.16 Kelvin. It's the exact same as the previous scales, the Fahrenheit and the Celsius. We just use different things to define what those scales are. We use the absolute zero, which is the lowest possible temperature, and then we also use the triple point of water. Now, to convert between Kelvin and Celsius scales, a Kelvin is equal to a degree Celsius. And in order to convert between those scales, we would say that the Celsius temperature is equal to the Kelvin temperature minus 273. We'll just say 273. All right, so for example, if I wanted to know what is absolute zero, in Celsius, then I would say, well, the temperature of the Celsius is 0 minus 273 Kelvin, or that's equal to minus 273 degrees Celsius. We wouldn't have that Kelvin there. All right, so whenever I want to convert between Celsius and Kelvin, I just subtract 273 from that Kelvin. But otherwise, the Celsius scales and the Kelvin scales, they have the same size of their degree. You understand what I mean? If I have a change in 1 degree Celsius and I have a change in 1 Kelvin, that's the same change in temperature. Now, 1 degree Celsius is not equal to 1 Kelvin, right? 1 degree Celsius is actually, well, 1 degree Celsius is not equal, but those changes in temperature are the same. Alrighty? What else? There it is. Let's try this quick test, if I can ever get it up. Yeah, I'll have it. I'm going to go ahead and start it. I think there's one right on the next page. Am I right about that? Just a second, I'll show it as soon as my screen unlocks. Well, folks, I can't seem to go to the next page. Yeah, I'll answer that question. It's going to reopen this, okay? All right, I'm going to stop the clicker. Did everybody get your answer in? Did everybody see the question? If you don't have your book, just ask the person next to you. Is everybody okay? I have to stop the clicker. It's going away at 1:30. 1:30. Okay, awesome. D is the right answer. Let's see if I get to the next page. go. Okay, good. So here I want to know what is the degrees in Kelvin, or what is the temperature in kelvins. So my T Celsius is T Kelvin minus 273, and I say 20 then degrees Celsius is what in Kelvin? I'll add 273 to both sides, and I get 293 Kelvin. So if you're ever out and it's a nice day, you can say, man, it's like 293 out here, right? Okay. Let's look at thermal expansion. You might not have seen thermal expansion before, but you're familiar with it at least. If you've ever driven over a bridge and you've seen something like this, whenever you go over one of these big bridges and you go, boom, 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 there's a little rhythmic bump that you have on the bridge, and you might look out your window and you see these metal grates that come together. Those are there because over time, over the day, over the course of the day, the bridge heats up and it cools off, and it has to move back and forth because as it heats up, it gets bigger, and those things will move closer to one another, these grates, and then as it cools off, it'll get smaller, and they'll separate from one another. So these grates are to allow for thermal expansion, which is just the expansion of a material when the temperature increases. Right. We'll see thermal expansion, or we've seen it in the temperature scales. Remember which of the temperature scales use thermal expansion as the means? Well, there are a couple actually. But the what now? Okay, the thermostat is one. What was the other one? You said it, I think. No, the thermometer, the mercury thermometer. The thermostat that has a little coil of metal wire, and then also the mercury thermometer has the mercury. When it heats up, it expands. So thermal expansion can happen in a lot of ways, or in several dimensions, but we're only going to look at linear expansion. Or not. For this. Okay, so our linear expansion is given by this expression. This delta L is equal to alpha L naught delta T. You have the equation on your equation sheet, so don't bother memorizing it. But you do need to know what these things mean. This delta L is the amount that it increases. So let's say I have an object, it has an initial length L naught, and then I heat it up by some temperature, delta T. I make an increase in length by delta L as it heats up. Like your bridge, or if you have a metal bar and you heat it up, it will expand. Now this alpha is called the coefficient of linear expansion, and it's generally found experimentally. So you heat up a material, and you see how much it expands, and then you can calculate that alpha. On your equation sheet, I have a table like this one that has different coefficients of linear expansion. You'll probably see a question, and we'll see one in the concept test, where I ask you how these things expand at different rates. So notice, for example, that glass and Pyrex, they have quite different coefficients of linear expansion by a factor of 3. That means that glass is going to expand at a faster rate than Pyrex. That might sort of pique your interest, because what is Pyrex known for? What do we use Pyrex for? And we use it for baking, right. So notice that Pyrex has a smaller index or coefficient of linear expansion than glass does. That allows you to heat its temperature more rapidly and to heat its temperature over greater ranges. And it won't expand as much and it won't crack. So we'll see some questions about that. You'll likely have some questions like that on the test where we ask, how does the linear expansion of different materials differ? And you'll have to look at their coefficients and interpret it from that. Oh, I think it was like a different alloy of steel. I forget. I'll make sure that it's okay for your equation sheet. What is up with this? Alright guys, I'm sorry. Okay, let's try this. Clicker question. I'm going to write the answers up here in case you don't have it. 996. So here we have a pendulum, and this pendulum has a rod of 0.25 meters and has a period of 1 second. And then that's at room temperature, which you know is about, what is it given? Which is 20 degrees Celsius. Then you heat it up to 320 degrees Celsius, and I want to know now what is the new period. So a couple different things that you'll need to do here is you'll need to find out how much it's expanded by increasing this temperature, and then figure out what is the new period. By the way, guys, on a multiple choice test, you should look at the answers first and just ask yourselves which of these are not reasonable, which A, B, C, or D is not reasonable. One or more of those. Why is B not reasonable?
Because it makes it smaller.
Right, because when you heat up this pendulum, it's going to make it longer, but if I increase L, that's going to increase T by some amount. We're not really sure by what amount. And that means that my period, which was 1 second, I think, yeah, it's 1 second, it has to be more than 1 second. So I can actually get rid of both A and B on this one and calculate, and then it cuts my chances considerably. I think I'll use 9.8 for G on this, so if you get a slightly different answer, that's okay. All right, let's do just about 10 more seconds. I'm going to stop at 3:05. Ask your neighbor. You're not sure. Looks like we're sort of split up on what the right answer is. I'll stop at 3:05. 3:05. Okay, let's see. I think D is right, but we'll just check. All right, so here, first thing you want to do is find out what is delta L. So delta L is equal to L naught alpha delta T. Take our L naught is 0.25. Our alpha is, for NVAR, is this material. And then my delta T is going to be 320 minus 20. So I get 0.25, 0.9 times 10 to the minus 6. And then I get 300 degrees Celsius. Now, notice here that I didn't convert it to Kelvin. You'll have to be very careful when you're working through problems, because sometimes you'll need them in Celsius and sometimes in Kelvin. And I know to put it in Celsius here because my units for alpha are in per degrees Celsius. So you'll just have to be careful of that. Look at the units that you're dealing with and make sure that they all jive together. So that dimensional analysis will be useful just to help you pick out what unit to use for your temperature. Let's see, when I did this, I got a delta L of 0.000675. Am I right about that? Yeah, so that gives me my new L of 0.2500675. And if I take that L and I put in here, then I get my D. Was it D? Yeah, so then I get my period of 1.004 seconds. Okay? You're going to have a problem where you just have to figure out how much does this thing increase in length when it has a change in temperature. There are some homework questions like this, and then, of course, you can look at the old test too and practice it, but it'll look something similar to this. Maybe not a pendulum in a clock, but something similar. All right. Now let's do, okay with this, folks? Well, we're going to come back to it in the concept test, but let's go on to the ideal gas law. What is that? All right, so remember we talked about the Pyrex and how that worked? Oh, I'm supposed to tell you a story about our wedding picture. So when we got married, like 13 years ago, 14 years ago, we got this picture, a really nice crystal picture for our wedding, because people give you gifts when you get married. I don't really get it, but they do. And we had this really nice crystal picture. And in our house, I'm from Mississippi, and so my wife's from Missouri. People from Mississippi, like, we know how to make sweet tea, right? Lots of sugar. It's not really that hard, but you just put a lot of sugar in it. But my wife, she doesn't know how to make sweet tea. So whenever in our house we make sweet tea, I would do it. And so you pour the tea into the pitcher, right? And then you put the sugar, and then you put the cold water. And what had happened when I poured the tea into the pitcher? What happened? It didn't shatter, but it cracked. And like my wife, she was across the room, and she could hear it crack. It's like, is that on your picture? Yeah. So what happens there is that when you put a hot liquid into some kitchenware, it will cause it to crack when you put a hot liquid inside of it, like tea. And note that Pyrex, remember we saw earlier that Pyrex and glass had different coefficients of linear expansion, that Pyrex had the bigger or smaller coefficient? It had the smaller, so that means that it's going to expand less when the temperature increases. It has a smaller coefficient of linear expansion, so that when you put hot water or hot tea or whatever, that it doesn't expand as much. But with glass, you get one side that expands, and then one side that doesn't expand. When you get this side expanding before this side, that's what causes it to crack when you put that hot liquid into it. Okay, we also see linear expansion in bimetallic strips. So you could have a question like this, where you have two materials, and you have to think about how they change shapes depending on the temperature. So let's look at this bimetallic strip. That is two pieces of metal that are welded together into a strip. I have steel on one side, I have brass on the other. They're at room temperature. If I heat that up, does the strip bend up or down when it's heated? Does it bend A, up, B, down, or C, neither? You'll want to think about which one will expand more when it's heated up. You'll need to look at those coefficients. And then ask yourself, when it's heated up, which way will this bend? For example, I don't know what their coefficients are, but if brass had a big coefficient, what would that cause it to do versus the steel? And then which way would it cause it to move? Up, down, or would it just stay where it is? All right, I'm going to stop in 5 seconds at 1 minute. I'll stop at 1:05. 1:05. Okay, good. Well, sort of good. A is the right answer. If I look back at the table, which of those has a higher coefficient of linear expansion? The brass has quite a bit higher linear expansion rate. That means that when you heat this up, this side is going to get longer than this side at a faster rate. It'll increase in length by more, and then also more quickly, it'll increase in length. And so if the brass side gets longer, that means that it's going to bend up, because I get, the long side on the outside, and then I get the shorter side on the inside. It'll cause that metal, that strip of metal, to bend upwards. If they were switched the other way around, it would bend down. Like if the brass was on the top and the steel was on the bottom, then it would bend downwards. So this is kind of nice, because now I have this device that will move depending upon what the temperature is. The more you heat it up, the more it's going to bend. Let's see. Yeah. So if you have one of these old thermostats, anybody have an old thermostat like this in your house? Most of you probably don't. You might have seen one at least, where you have a thermostat. You usually have like a round dial on top of it. If you take that round dial off, you'll see a coil like this. This is a bimetallic strip. And on that bimetallic strip, depending upon the temperature in the room, it'll either get tighter or it'll relax, depending upon the temperature of the room. And then that'll cause your heater or your air conditioner to either come on or go off, depending upon how you have it set. So here, in this thermostat, I have a bimetallic strip. Very much like the one that we had before. All right, let's try this quick test. This is a steel tape measure. It's used to give measurements at very hot temperatures. But then I use it to measure something at room temperature. At this new room temperature, at this lower temperature, how will its length measurements will be affected? Will the measured lengths that you measure at lower temperature be large, accurate, small, or is just not enough information? Think about how this ruler will change shape when it goes to this lower temperature, and how that affects our lengths.
Because when it's used in hot, it expands and rates more. So it has to be smaller than the temperature for it to be accurate when it's measuring.
Okay, y'all are pretty much evenly split. You'll want to think about these problems because you'll probably have one something like this, and we'll see some variations on the concept test. But you want to think about these problems: what happens to the device, and how does that affect your measurement? I'm going to stop here in just a moment. I'll stop at 125. 125. Okay, A is the right answer here. That's good. Imagine that I have this ruler. I have this ruler. It's at really hot temperatures right now because it's designed for that. And let's say that I have some device and I measure it to be 1, 2, 3 units long, right? Now I go to cold temperatures. And what's that going to happen to the ruler when I go to cold temperatures? It's going to get bigger, smaller. It'll get shorter, right? Because it's no longer experiencing this expansion. So it's going to be shorter. And now my marks are going to be closer together. And now if I put this object that I had up here up next to this new ruler, notice it's going to be measured not 3 units long, but 4 units long. Although this is not the correct measurement because my ruler has gotten smaller and it's just not calibrated properly anymore. Okay. Don't worry, we'll see some other questions like that that are dealing with sort of those ideas regarding linear expansion. All right, let's look at the ideal gas law, and then we'll wrap this chapter up. The ideal gas law deals with low density gases, but you know, most gases are low density. That means that the molecules or the atoms of the gas aren't really going to interact with one another. The atoms will move randomly, and they exert no forces on one another. That means they don't, they don't collide. They just don't really interact with one another. We often use moles to express the amount of a gas. And of course, Avogadro's number, which you've heard before, I'm sure, gives the number of particles, atoms, or molecules in a mole of gas. A mole isn't particular to a gas. Like you could have a mole of students, right? Can we get a mole of students in this room? No, because there'd be a lot of students. But the president would love to have a mole of students at Nichols State. But that's not going to happen because there aren't that many people in the world. But anyway, you could have a mole of students. You could have a mole of whatever. But we use it to describe gases. Avogadro's number, which is the number that is in a mole, is 6.02 times 10 to the 23rd. And that's just the number of particles, molecules, or atoms per mole. This, by the way, is based on the number of atoms in 12 grams of carbon-12. If you want to know that. But that's where we get that number from. I won't ask you that, but just sort of for your own interest. All right? The molar mass of a particular substance is equal to the mass of one mole. So the number of moles then is the mass of the substance divided by the molar mass. So if I want to know the number of moles that I have, I just take the mass of whatever I have and I divide it by the molar mass, because the molar mass is just equal to the mass of one mole. That's the value that you'd be given. And then to calculate the mass of an atom, I would take my molar mass, which is the mass of one mole, and I'm going to divide it by the number of particles in that molar mass. So for example, if I'm looking at helium, which has 4 grams per mole, divided by 6.02 times 10 to the 23rd, I get 6.64 times 10 to the minus 24 grams per atom. You don't need to know these values, but you do need to know how to take our molar mass and our Avogadro's number and figure out what is the mass of an atom. Or if I give you the mass of the substance and the molar mass, how to figure out what is the mass of that, or how many moles I have of that substance. Okay? Stuff that you should have done in chemistry, I think. Am I right about that? All right, let's try this quick test. Which has a greater number of atoms, a mole of nitrogen or a mole of oxygen gas, and then I give you their molar masses there. Notice oxygen has a bigger molar mass than nitrogen. All right, folks, I'll stop at 1 minute, or we'll go to 105. 105. It's 5 seconds. Okay, good. It is both the same, because a mole is a mole, right? It doesn't matter what their molar mass is. Here we're just asking for the number of atoms. And if I have a mole of nitrogen or a mole of oxygen gas, then they're both going to have the same number of particles. Now, if I asked you which had the bigger mass, it would be the oxygen, because it has a bigger molar mass by that amount. Okay, now let's look at the ideal gas law. Ideal gas law is really a combination of two laws. It's a combination of Charles and Boyle's law. Charles' law just says that V is proportional to the temperature. That if I increase my temperature, my volume of a gas will also increase. So as temperature increases, so does the volume. And remember, we had that base for one of our temperature scales, that the volume of a gas at a constant pressure was one of our ways to measure the temperature. And then Boyle's law says that P is dependent upon 1 over V. So as volume increases, the pressure will decrease. That sort of makes intuitive sense, that if I have a container of gas, and I keep the same amount of gas in that container, but I make the container bigger, then the pressure is going to decrease. Because you'll just have the molecules of gas that we move farther apart, and they'll exert less pressure on the sides of the container and on one another. So if I put these two together, the ideal gas law is written like this. It says that PV is proportional to T, and it's actually proportional or equal to the NR times T. So I've added in two extra terms here. The N and the R, but this PV is proportional to T comes from Charles and Boyle's law. Here R is the universal gas constant, 8.314. That's in joules per mole Kelvin. So be careful when you're dealing with this ideal gas law that you have your temperature in what units? In Kelvin. Listen, if you're unclear on the test, just look at the units of the things that you're using. So if you're doing coefficient of linear expansion, which is in degrees Celsius, you'll need to be in Celsius. If you're doing it in ideal gas law, where you have this universal gas constant, then you'll need to be in Kelvin. Just be careful with your temperature. Make a little mental note that you check that. And of course, N is what we've already seen. It's the number of moles. So you'll have a problem for the ideal gas law. Hopefully everybody will get it right, where I give you a certain pressure, a certain volume, a certain temperature or whatever, and I ask you to solve for one of the unknowns. The only trick is, or no trick, but the only complication is you might want to check the temperatures to make sure it's in the right units. Because often we give temperatures in Celsius, not in Kelvin, even though Kelvin's the SI unit. But often we give temperature in Celsius, and so you'll need to do that conversion. Okay? Just be careful with that. We can also express this with the number of particles. No, you're not really going to see this, but you've seen this before, I think. You're not going to, don't worry about this for the test, but I can just sort of change my N and my R into this N, which is now the number of particles, and K, which is Boltzmann's constant. And then I just sort of change the way I define that constant. But don't sweat it. All right, I think that was it for this chapter. Am I right? Oh, there's a couple quick tests. Okay, let's do those. They're a good indicator of what you'll see. Be careful with your units. You'll have to make a couple of conversions. Remember your various SI units for measurements and pressure, volume, and temperature. If you finish this one, go in and do the next one. I think there's one more. We'll do about 15 more seconds. I'm going to stop at 2. I'll stop at 2:15. 2:15. Okay, I think B is right. Let's see. So I have this container. It has 0.1 cubic meters. So that's my volume is 0.1 cubic meters. It holds 10 moles of gas. That's my N, which is 10 moles. The pressure is 1.5 atmospheres, but I need to convert that into pascals. So remember, 1 atmosphere is 100,000 pascals. So I'll convert that to 1.5 times 10 to the 5th pascals. And then I want to know what is the temperature. So I say PV equals nRT. T is PV over nR. And I get 1.5. 0.1, 10, and 8.314. And that gives me the temperature. What do I get when I do that? What is it, Chandra? 0.0018. All right, but that is in Kelvin. You have to be careful. It's in Kelvin. So that means that my temperature is going to be really low. Is that right? Does it come out to 0.0018? Let me double check. No, I get 180 when I do that. I have to check. I think maybe your order of operations are wrong on that. So I get 180 Kelvin, but then I need to convert that into Celsius, and I get which of these? I get B, right. So remember doing your unit conversion, so we get B there. All right, so B is right. And now let's try this last one. They contain the same gas. 2 identical cylinders at the same pressure contain the same type of gas. If A contains 3 times, which cylinder has the higher temperature? You want to think about your ideal gas law here. All right. Let's see. We'll stop at 1 minute or 105. Let's go to 105. Okay, so the one that has 3 times as much gas, if N goes up for the ones that has 3 times as much gas, that means that T is going to go down. So the one with the higher temperature will be the one with less gas. So B is going to be the right answer. We've done these types of questions before where you look at the variables in the equation and then ask yourself, what happens if I change one of these variables? If I make N go up, then that means the temperature goes down, keeping pressure and volume constant. And so the right answer would be B, that the one with the smaller N has the higher temperature. Okay? All right, so what I'm intending, I know there's sort of a whirlwind through ideal gas law and temperature scales and linear expansion, but that is everything in the material. So what I'm intending for Wednesday and Friday is this. First of all, I'm going to post your clicker points, your class participation. Many of you have already maxed that out, so I'll post that and you'll sort of get a feel for where you are, or you'll know where you are. But on Wednesday, I'm not going to have class, so to speak, but if you want to come in and we can go over the concept test for this chapter, then certainly do so. And then also, if you're short on your clicker questions, you can come in at that time and pick up some extra points, because there are like 15 or 16 questions on that. Now, I will post the solutions to those, so if you decide not to come to that class, and that's fine, I understand, then you can do so, and then you can pick up the solutions later. But if you're short on your class participation, then by all means, you should come on Wednesday. And I'll be here, and I'll be in this room. Yeah, this Wednesday. But I expect there to be a light crowd. And then on Friday, we'll have a review for the test, which is on Monday. So on Friday, we'll spend that day reviewing for the test. Okay? You have any questions about what to expect? I expect to see all of you on Friday, but then some of you may be on Wednesday, okay? You all have a great day.
The normal time to use.